I'm Marilyn Wolf. This is Computers as Components, Chapter 1. What is an embedded computing system? An embedded computing system is a device or machine that includes a programmable computer but isn't itself what we think of as a, quote, computer, end quote. So your laptop is not an embedded system. But you do have all sorts of things that have computers in them. Your cell phone, it's a very powerful computing system. Your car has a whole lot of computers in it. Even the electric plug on the wall that you plug your computer into, on the other side of it is a very complex computer system that keeps the electric system running. So embedded computer systems have to interact with the real world, and that means we need a lot of specialized techniques in order to design them. One of the things that we do is take advantage of the application characteristics when we design the system. So we may not put in all sorts of features that we don't really need. When you're dealing with real time, when you're dealing with low power, putting extra things in may make it harder for the system to do what it has to do in the time and the energy it has. So here is a block diagram for a generic computing system. This could be the computer in your laptop, or it could be an embedded system. So we have a CPU, we have a bus that connects the CPU to some memory and some I/O devices. And of course these I/O devices have some analog electronics, maybe some mechanical components, but the input and output digital logic interfaces to the CPU. Now in a lot of cases we can put everything in here, the processor, the memory, the I/O devices, on a single chip. And that's what makes computers very powerful for manipulating the real world. What are some examples of embedded computing systems? Your cell phone has several very powerful computers in it. A printer has several computers in it that are doing real-time calculations. Your car has computers that control all the critical systems as well as provide you with entertainment. Same thing with airplanes. Airplanes rely on a network of computers. Digital television does a lot of computing at very high data rates in order to provide you with HDTV. A lot of household appliances use computers. So if we look at the early history of embedded computing, it's actually pretty well wound up with the history of early computers themselves. For instance, one of the first computers that was built, the MIT Whirlwind in the 1940s, was originally designed to control an aircraft simulator. But the Whirlwind was a computer the size of a room running on vacuum tubes. When we became able to put a computer, even a simple computer, on a single chip, that's when opportunities for embedded computing really exploded. The first single chip microprocessor was the Intel 4004 in the early 1970s. That was used originally to build calculators, and it went on to be used in all sorts of other devices. Another early example of using a microprocessor to do complex functions was the HP 35 calculator, which used several chips but put them together to build a microprocessor to do very sophisticated numerical algorithms for scientific arithmetic. And it did this in the early 70s in a handheld device. Cars started to use microprocessor-based engine controllers in the 1980s. They moved from mechanical controllers, which included things like distributor caps, to having microprocessors that actually determined the fuel-air mixture, determined when the spark plugs flew, actually controlled the engine. Not only did they control the basic operations, but they had several modes of operation. For instance, in warm-up phase, the engine might run a little faster. Then in idle, the engine would slow down. Cruise was one setting for the engine. When you climbed a hill, you used a different setting for the engine. Why did car manufacturers do this? Well, they were faced with the need to both lower the emissions of these engines and provide better fuel efficiency. And the mechanical controllers simply weren't flexible enough to meet these demands. So they had to use sophisticated algorithms running on microprocessors in order to meet the demands on modern car engines. So we'll see a couple of terms when we talk about the hardware we use. A microcontroller usually means a single chip system that includes the processor, I/O devices, and some memory. A digital signal processor, or DSP, is a microprocessor optimized for digital signal processing, and we'll talk later about what that means. Now you'll see a wide variety of sizes of embedded computers in embedded systems. We typically measure the size of the computer. A simple way to do it is the word size. So we have 4 and 8-bit processors, 16-bit processors, 32-bit processors, and even some 64-bit processors. So what do these computers do? Well, if you think about a simple appliance like a microwave oven, it has to run the timer, turn the device on and off, turn the lights on and off, that sort of thing. You look at a still camera or a video camera, it's got to do a lot of manipulation of the image, exposure control, compression of the image. And so these cameras usually have several processors in them. They might have microcontrollers and DSPs, and they're all working together to do all the image capture, compression, and so forth. Digital television, once again, we usually have programmable processors plus some hardwired logic because of the high data rates and the complex algorithms. If you look at a car, a typical high-end car today will have at least 100 microprocessors in it. Some of them do very simple things like have 4-bit microcontrollers to check whether the seatbelt is locked. But you'll also have microprocessors running the engine, the brakes, running the dashboard devices, running the entertainment system. But even a low-end car today has at least 20 microprocessors in it that are running the critical systems of the car. So it's very difficult to get away from computers when you're in your car. Let's look at one example in the BMW 850i. Two related systems. The anti-lock brake system, or ABS, measures how fast the wheels are turning, figures out if they're skidding, and then pumps the brakes if necessary to break the skid. Automatic stability control with traction, ASC plus T, controls the engine to improve the stability of the car so it doesn't turn over. So these two systems work together and need to communicate. And so the ABS system had to be designed to talk to the stability control system. So if we look at a block diagram of the car for the ABS, each wheel has a sensor, okay? And that goes back to the analog brake system that looks at all 4 of the wheels simultaneously, figures out if it needs to apply the brakes to any of them, and then uses the hydraulic pump to control the brakes and actually do the braking that's required. So in summary, embedded computers are everywhere. They run all sorts of devices. They provide critical functions. And they provide sophisticated user interfaces that we've come to expect. So embedded computers can be very simple devices, but they can also be very complex, high-speed devices that are running very sophisticated software.